All right, this is number 4 from the review problems, and this is a statics problem. So that means that some of the forces and some of the torques are equal to 0. So this is, I'll just read it, a 5-kilogram cat and a 2-kilogram bowl of tuna fish are at opposite ends of a 4-meter long seesaw. So we have to draw an extended free body diagram of the forces acting on the seesaw. And then how far to the left of the pivot must a 4-kilogram cat, so a second cat, stand to keep the seesaw balanced. Okay, so let's look at our givens and finds. This is 4 and given. So we have, we'll call it mass of cat 1 is equal to 5 kilograms, and mass of cat 2 is equal to 4 kilograms, and mass of the fish is equal to 2 kilograms. Now we see that the length of our seesaw is equal to 4 meters, and we have cat 1 and the fish are, so we'll call that R1 for cat 1 is equal to L over 2, which is equal to 2 meters. So that's how far away the cat is from the pivot point in the center. And then R2 is the second cat, and we're going to say we don't know what that is yet. And then we'll have R for the tuna, for the fish, is equal to the same L over 2, which is equal to 2 meters. Okay, and we're trying to find R2. Okay, so we've got our picture. We'll just draw. So I'm going to use this picture, but you should draw it yourself on an exam. But I'm just going to draw the free body diagram, the extended free body diagram over here. So I've got this pivot right in the middle, and then I have the force of, I'm not even going to draw the pivot. What I'm going to do is say the pivot is a normal force that points up right at the center. That's my normal force. And then I have, this is my force of the fish. I have this force of cat 1, and then I have this force of cat 2. So notice I'm using my the fulcrum for the seesaw as my point about which to rotate. So this is going to be, I'm going to call this O for my point about which to rotate. Okay, so the first thing I know is I know I have to do the sum of the forces are equal to 0 and the sum of the torques are equal to 0. That's the model, and so anytime you have a statics problem and an extended free body diagram, you want to write these things down. So we'll start with the sum of the forces. So we've got, we'll use the forces up as positive and the forces down as negative. So I'm going to have force of the normal minus force of the fish minus force of cat 1 minus force of cat 2 equals 0. And then for the sum of the torques, I want to think about what is causing my beam or seesaw to rotate. And so I'm rotating about this point right here. I know I don't know anything about my fulcrum. I don't know the force that it's pushing up on the my seesaw. So that's why I use that as a fulcrum, because I know these other things. I know the mass and gravity, and I know the mass and gravity, and I know the mass and gravity here. I don't know R, but then that just gives me one thing to determine, and that's what I need. So what I want to do is I want to see which of these forces causes my seesaw to rotate counterclockwise. Right, so if I just had this force and the others weren't here, it would cause my seesaw to rotate clockwise. So that's in the negative direction. So these two forces cause my seesaw to rotate in the counterclockwise direction. So I'm going to start with those. So some of the torques are equal to 0, and I'm going to say the force of the fish plus the force of cat 2, and then minus the force of, hold on a second, I forgot to add in my R's. Let me back up a second. So I know torque is equal to R cross F, which is equal to R F sine theta. But all of these forces are perpendicular to my beam. So I know that means that my angle here is 90 degrees, 90 degrees, 90 degrees, 90 degrees. So all of these, sine of 90 is equal to 1. So really my torque just becomes RF for each of these terms. So for the force of the fish, I'm doing R So the distance, this here is my distance to the fulcrum. So this is going to be my L over 2, or 2 meters. And the distance from here to the first cat, that's going to be 2 meters. And so the thing I don't know is this distance from here to here. And that's going to be R2. And that's what I'm looking for. So the force of friction times, I'm just going to leave it in 2 meters. This is one of those cases where I'm just going to, well, we can actually use a variable here because I know that my fish is 2 meters. So I'm going to call R fish minus, so the fish cause it to rotate counterclockwise, or plus R2 times the force of the cat, 2, and then minus, so these two both cause it to rotate counterclockwise, but this one causes it to rotate clockwise, so that's why it's a minus, R1 F1. And then the last thing is the force of the normal, so that's at the center, and so I'm just going to write plus R of the fulcrum, so let's just call it O, force of the normal, equals 0. And so right off the bat, since this force of the normal is right at the fulcrum, my R is equal to 0. So that just goes away. Okay, and now the thing I'm looking for is R2. So I'm going to try to get R2 alone. So R2 F2 is equal to, and in order to bring this over to the other side, I have to add R1 F1 and subtract R2 RF FF. Okay, so my R2 then is equal to R1 F1 minus RF FF over F2. So R2 is equal to, R1 is 2 meters times, now F1 is, so let's not do this yet. Still need to be plugging in. So R1 M1G minus RF M fish G over R2, or nope, yes, not R2, just F2. So this is just going to be M2G. And notice all my G's cancel, which is nice. So R2 is equal to R1 M1 minus RF MF over M2. So plugging that in, we get R1 is 2 meters times 5 kilograms minus 2 meters times the fish is 2 kilograms over 4 kilograms. So R2 then is equal to 1.5 meters. So that's the answer I'm looking for. How far does it need to be to the left? So here, this is going to be 1.5 meters, and I didn't even have to use the sum of the forces equation. Sometimes I do, sometimes I don't.